Almost any physical quantity one measures is not a pure number, but a number times some units, usually involving time, distance, mass, and/or electrical charge. There are many reasons to carry these units around in calculations, the most basic being for sanity checks, but also, famously, because different people might measure with different units. This isn't a new problem either. But I want to focus today on a positive reason to carry around units. Quantities in the same units should be compared. What does miles per gallon mean? A gallon is a unit of volume, which is distance cubed. So 30 miles per gallon is an inverse area. 30 miles per gallon times 5280 feet per mile times 1 meter per 3.28 feet times 1 gallon per 3.728 liters times 1 liter per 1,000 centimeters cubed comes out to 1 over 0.028 centimeters squared, or 1 over 0.28 millimeters squared, very nearly the thickness of a standard embroidery thread. What does this thread have to do with a car that gets 30 miles per gallon? We can rewrite, showing us that this volume matches that of a mile of thread. Imagine if gasoline were extruded from cars rather than burned, i.e. if car exhaust were a solid instead of a gas. Then our calculation is of the cross-sectional area of that solid. How many cars drive by your house each day? How much gasoline thread would they have left there by day's end? The Holland Tunnel leaving Manhattan sees 90 to 100,000 cars a day, so let's call it 100,000 cars a day. Its dimensions are 6 meters by 3.81 meters. How long before it would be completely clogged with thread? 1 car per 0.28 millimeters squared times 6 meters times 3.81 meters per 1 tunnel times 10 to the 3 millimeters per 1 meter squared times 1 day per 10 to the 5 cars is about 2915 days per tunnel. Making this more human readable just amounts to multiplying by a unit converter. That seems long enough that the Port Authority would have time to clean out the tunnel periodically. Unless all the calls were crawler transporters for the space shuttle, in which case the tunnel would fill up every 18 hours. We think of distance and time as somehow more fundamental than other combinations one can make of them, like speed, which is distance divided by time. But the most easily measured physical constants are often not in these fundamental units. Puzzle: what is the extremely ridiculous meaning of this length of time? From here, it's easy to construct a unit of length as well. If we focus attention on what's called the exponent vector, we see that extracting fundamental units from combinations thereof comes down to a linear algebra problem. Here it amounted to computing the inverse of this matrix. One of the things one most wants to compute about a matrix, more generally, is its kernel, those vectors it annihilates. Here are 4 fundamental constants whose exponent vectors are linearly dependent. Consequently, there's a combination of them, which carries a 2 coefficient traditionally, which has no units. It is a pure number. Physicists worried about this alpha a lot, called the fine structure constant, even going as far as to consult Carl Jung for help. But it turns out that the charge on the electron isn't really so constant after all. The closer you get to the electron, the less subject you are to a phenomenon called charge screening, and the perceived charge goes up. In accelerator experiments, in which particles get especially close, the fine structure constant gets down into the 120s. I went looking for other weird units. A lot of them involve square roots. Fracture toughness is measured in pressure, which is force per area, times square root of length. Noise amplitude spectral density is in volts per root hertz. Scattering measure in astronomy is in kiloparsecs, which is distance, times meters to the negative 23rds.